All right, let's jump straight into this explainer. Today, we're tearing down the blueprint of one of humanity's absolute most impressive feats, the massive gravity dam. And we're going to look at this specifically from the perspective of the engineers on the ground. The folks who actually have to guarantee that these megastructures won't buckle against the overwhelming forces of nature.
Now, to put the sheer scale of this into perspective, think about this number, 125 years. If engineers hadn't come up with a totally radical way to cool the millions of cubic meters of concrete inside the Hoover Dam, it literally would have taken 125 years for that thing to cool down on its own. Without us stepping in, the intense chemical heat trapped inside would have caused catastrophic cracking. It would have compromised the entire project. So yeah, building a dam is a whole lot more complex than just pouring concrete into a giant valley.
To understand exactly how we prevent those kinds of catastrophes and build these megastructures safely, we follow a very specific chronological blueprint. 1. Caming the river flow. 2. Foundation and plinth construction. 3. Pouring the mass concrete. 4. Cooling the concrete core. 5. Defending against internal erosion. And finally, 6. Future-proofing and emergency plans. Let's get right to it.
Number 1. Taming the river flow.
The crucial first step is managing the immediate roaring threat to any construction site, millions of gallons of rushing water. You can't build a massive foundation underwater. So what do? We literally have to move the river. And we do this with a pretty reliable 1-2-3 punch. First, engineers drill a massive diversion tunnel straight through the rock, often using heavy explosives, to route the water completely around the construction zone. Next, during low water levels, we build temporary blockades called cofferdams both upstream and downstream. This funnels the river right into that tunnel. Finally, we just pump the enclosed zone completely dry.
Now that the riverbed is totally exposed and bone dry, we're hit with our next huge challenge. How do we actually prove that the earth beneath us can hold the mind-boggling weight of what we're about to build?
Number 2. Foundation and plinth construction.
Engineers are out there hunting for invisible threats long before the real building begins. We pair intense subsurface investigations with deep rock testing to scope out seismic vulnerabilities. We're talking earthquakes, fault offsets, liquefaction, the works. At the same time, we have to fight off upward water pressure and internal erosion, right? So we install these highly specific granular filters directly onto the foundation. This setup safely captures seepage, but without letting the essential soil wash away.
To really seal the deal, we clear out all the loose rock and construct what's called a plinth. Think of the plinth as the ultimate anchor point. It's this deep concrete foundation totally embedded into the natural walls and floor of the valley. Its one job: lock the structure into the bedrock and stop destructive edge leaks dead in their tracks.
Number 3. Pouring the mass concrete.
With our foundation rigorously tested and locked in tight, it's time to build upward. Take a look at the Grand Coulee Dam, for example. This is exactly what a gravity dam is. It uses its sheer, massive weight to just muscle back the immense pressure of the reservoir water. The downstream surface even has this specific concave curve designed to absorb that constant punishing hydraulic pressure and deflect it safely right down into the ground.
Traditionally, these megastructures use conventional concrete, but let's be real, that's incredibly expensive and kicks out a ton of CO2 emissions. So to cut costs and lower the environmental impact, modern engineers often swap that out for roller compacted concrete, or RCC. This material gets compacted in layers by heavy vibrating rollers, it uses a lower cement ratio, and it dramatically speeds up the build without sacrificing an ounce of strength. Sometimes engineers even use a thin layer of high slump bedding concrete just to seamlessly bond that RCC straight down to the bedrock foundation.
Number 4. Cooling the concrete core.
Here's the thing. Pouring millions of tons of any concrete introduces a serious hidden enemy. When cement mixes with water, you get an exothermic chemical reaction called hydration. Basically, it generates a crazy amount of heat. And because the concrete is just so incredibly thick, all that heat gets trapped inside the monolith. The core gets insanely hot while the outside cools down. That creates a huge temperature gradient that literally threatens to crack the entire dam wide open. To beat this heat, we actually learned a massive lesson from the Hoover Dam. We don't cast the concrete as one giant continuous block. No way. Instead, we pour it in smaller, individual, interlocking blocks, usually around 15 by 15 meters wide and maybe 1.5 meters high. This vastly increases the surface area so the heat can dissipate way faster. It completely prevents a thermal meltdown. Later on, we go back and grout all those joints together to restore that solid monolithic strength.
But just breaking it into blocks, that's not enough.
We have to actively cool this thing from the inside out. We embed hundreds of miles of 1-inch steel cooling pipes right inside those blocks. It's an ingenious two-stage cooling loop. First, we pump cool natural river water straight through the pipes. Then, we flip the switch and start circulating mechanically chilled water from massive on-site refrigeration plants. We're talking plants capable of producing 1,000 tons of ice every single day. This setup safely cures the concrete in a matter of months rather than centuries.
Number 5. Defending against internal erosion.
Once the structure is built and cooled off, our job shifts to long-term defense, specifically defending against the silent killer of dams, internal erosion. We build sophisticated internal defense systems right into the body of the dam itself. We've got granular filter diaphragms that grab seepage water without taking the soil with it. And for dams over 30 meters high, we literally build physical inspection galleries deep inside the concrete. This lets inspectors physically get in there, monitor structural behavior, watch for seepage firsthand, and drill, drain, and grout holes to relieve pressure. Now, because these galleries are dark, damp, and super claustrophobic, personnel have to follow extremely strict confined space safety procedures. They rely on specialized ventilation and constant monitoring equipment just to stay safe while working deep inside the belly of the megastructure.
Industry data tells us exactly why all this is so absolutely crucial. Most concrete dam failures actually stem from foundation stability problems. Catching foundation anomalies and seepage early, using those galleries and monitoring systems we just talked about, is literally the key to preventing a catastrophic failure.
Number 6. Future-proofing and emergency plans.
No matter how perfectly we engineer a dam today, we have to prepare for the absolute worst-case scenarios of tomorrow. First off, no engineer works in a vacuum. A huge part of modern safety relies on rigorous, external, independent peer reviews. We're constantly running potential failure modes analyses, or PFMAs. These independent assessments basically guarantee our math holds up to reality and that we haven't missed any glaring blind spots in our belts and suspenders approach to safety.
We also have to pivot our designs based on rapidly changing hydrological data. Take a recent study by a hydroelectric developer in Iceland, for instance. They figured out that because of increasing glacial melt, we just can't rely on historical water data anymore. They concluded that modern dams must be over-installed, meaning we have to build spillways in capacities today that are explicitly designed to handle the completely unprecedented floods of tomorrow.
And because nature is entirely unpredictable, we set up ironclad emergency action plans. We meticulously document the true as-built conditions of the dam. We constantly reassess our capacities if the land use upstream ever changes. Most importantly, we heavily train on-site personnel to instantly spot actionable warning signs of failure, and we lock in incredibly tight, rapid communication channels with local emergency responders for extreme flood events.
This whole journey, from taming a rushing river to operating a heavily monitored megastructure, leaves us with one critical thought. Engineering is never truly finished. We've mastered the heat of hydration, we've learned to build colossal plinths, and we know how to map subsurface rock. But as our climate shifts and water flow patterns become more and more extreme, we have to constantly adapt our methods to match the sheer power of an ever-changing planet. So, what new engineering marvels will we need to design next?